I'd like to look at one more example today where we're going to give some bounds on the error for the approximation of root E using the third degree Maclaurin polynomial, which tells us that our center is at x equals 0. I'm going to start with the third degree polynomial, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now we're trying to approximate square root of e, or e to the 1/2. That's an indication then that the x value at which we're going to evaluate this polynomial is 1/2. So I have 1 plus a half plus a half squared divided by 2 factorial plus a half cubed divided by 3 factorial. I would put that in my calculator, and it's 1.646 and more. So I want to get some idea about what the error would be. We know that our remainder formula is f, the n plus first derivative at some c. That c, once again, that's always the big question. What is that value c? That c we're not going to know, but it is some value c on the interval from a to f. Our a value again is 0. Our x value is 1/2. So I know I have 1/2. And since I had taken 3 derivatives to create that third degree polynomial, this would be to the 4th power. I'm going to divide by 4 factorial then as well. And then again, as always, this is the big question mark. So we're looking at putting some bounds on this 4th derivative. So we know that the first derivative of e to the x is e to the x and so on. The 4th derivative is also e to the x. So we want to take a look at this graphically and see if we can get an idea to put some bounds on that error. Remember, it's somewhere between, open here, somewhere between 0, the center, and x, which x is 1/2, which is where that maximum occurs. But when we look at this function, e to the x, we can see that it's increasing on that entire interval. So what I've done is I've taken a look at comparing it to another exponential function, and I'm going to look at several different bases until I have something reasonable. Turn that on. Now we can see that a to the x on the interval from 0 to 1/2 is less than e to the x when a is 2. When a is 3, it's greater. When a is 4, it certainly is. So I could use actually any one of those values that makes sense. Evaluating that x equals 1/2 is going to be where I am maximizing that error. So let's take a look at this again. Now, I could certainly use root 3 because I saw that that was greater. But if I really want to be able to evaluate this easier numerically, I might want to use the square root of 4 because that's 2. And then I've got 1/2 to the 4th divided by 4 factorial. In this case, it simplifies to 1 over 192. And in this case, I would just write this as root 3 over 384. So either one of those would be appropriate. It is just giving some bounds on the magnitude that are reasonable and that makes sense.